Hey everyone, Victor is here, your organic chemistry tutor, and today I want to talk about the alkynide ions, which are one of those magic nucleophiles that you'll use to make new carbon-carbon bonds. In this video, we'll talk about how to make those nucleophiles and what sort of reactions you'll see for those species. And while these nucleophiles might seem like a magic solution for all your carbon-carbon bond formation needs, they do have their limitations, which often pop up on the test to trick students and make you lose points. So grab your cup of coffee and notebook to work through the examples with me, hit that like button for good luck on the test, and let's get started. And the first thing that we need to get out of the way is how we make those alkynide ions. Typically, we're going to have a terminal alkyne, the one where the triple bond is at the end of your molecule, reacting with a strong base which will deprotonate our substrate. And the big question here is, which base should we use? Or in other words, how strong the base needs to be? Well, to answer that, we need to know how acidic the terminal alkynes are to begin with. And if I peek into my pKa table, I'll see that the terminal alkyne's pKa value is somewhere around 25-26, which means that our terminal alkynes are not particularly acidic and will require a very strong base to nick that proton off it. If the pKa value of my acid is 25, the pKa of my conjugate acid must be significantly larger than that. And among the most common bases, we'll see the amide anion, we will also see a hydride, and also we will see the alkyl ion. The typical one you'll see in your course in most cases is going to be an amide, so that's going to be your usual go-to. And of course, since amide need a counter ion, the typical actual compound that you'll see written above the arrow in your reactions is going to be sodium amide. So if I were to use a real example here with real molecules, I'll treat a propyne, the 3-carbon chain with an alkyne at the very end, so I'll treat that propyne with sodium amide, giving me a corresponding alkynide anion and ammonia as products. So this one is going to be my alkynide, and of course NH3 is my ammonia. And of course, to make sure that this is indeed a favorable reaction, we can estimate our equilibrium constant by the same way we do it for any other acid-base reaction, by comparing the pKa values for our acid and the conjugate. In this case, the numbers would be roughly 25 for my terminal alkyne, just what I've mentioned a few moments ago, and for my ammonia, for my conjugate acid in this case, that value is going to be around 36. So that gives us the equilibrium constant being roughly 10 to the 11th power, if I can do my math correctly, which is highly favorable. So, okay, we've made our alkynide ion, cool beans, what next? Well, those compounds are strong nucleophiles and they're equally strong bases, so they will react with a whole bunch of different electrophiles. So, for instance, the first reaction that you'll see in your class will be a reaction with the primary alkyl halides. This reaction is a simple SN2 reaction with a small, well, actually not so small caveat. The reaction only works for primary alkyl halides. Alkynide ions fall into a category of nucleophiles which are also extremely basic. And when it comes to the substitution elimination reactions, when we are analyzing our reactions, we know that whenever we have a reagent which is a base and a nucleophile at the same time, they only perform SN2 reactions on the primary alkyl halides. In the case of the secondary or, of course, tertiary alkyl halide, the major pathway for the reaction is going to be an E2 reaction and not SN2, which means that if you were trying to attempt this reaction, you will not see substitution here. Instead, we'll end up with an alkene as the major product via the elimination mechanism, E2 here, of course. This is a common place where the students get tricked on the standardized exams like ACS and MCAT because not every instructor points out this this very important limitation. And to add insult to injury, some instructors completely ignore this huge limitation, which is my personal pet peeve, but I digress. So remember, if you want to use this reaction to make a new carbon-carbon bond, it's better be a primary alkyl halide that you're reacting it with. And depending on which textbook you're using in your course, you could also encounter a reaction of alkynide ions with epoxides. These reactions going to make alcohols where the OH group is one carbon removed from the alkyne. So I have my OH group over here, and I have one more carbon in the middle, in between the triple bond and the OH. And this type of reaction will require the acidic workup to actually put the hydrogen, or I should say proton, on my O- after the nucleophilic attack. You might also see a reaction with aldehydes or ketones. This one yields alcohols with the OH group on the adjacent carbon to the alkyne. But unless you guys are using the Clyden's or Cortis textbook, you most likely only see the reaction with the alkyl halides when you are just talking about this reaction in class, and maybe you will see the reactions with epoxides and aldehydes and ketones later on in the course, because those functional groups and chemistry of those is typically covered in the end of the first and the beginning of the second semester. Alright, so how would you use this chemistry in your class actually? Well, mostly you're going to use that as a starting point in a multi-step synthesis. Let me illustrate with an example. If I start with the simplest alkyne, ethylene, we can dress it up, so to speak, with different alkyl groups. First, I'll start by deprotonating it with sodium amide. Then I'll treat it with a primary alkyl halide, like for instance a butyl bromide, adding the alkyl chain to one side of my molecule. After that, I'll deprotonate it again with another equivalent of sodium amide, making another alkynide anion, which I'll react with another primary alkyl halide, giving me a rather big and complicated molecule with an alkyne functional group right in the middle over here. And since alkynes are a very synthetically versatile functional group, I can further convert this molecule into a whole bunch of other interesting targets. So for instance, I can make an alkene from it, or I can make a ketone, or I can even make a tetrahalide and a whole bunch of other things. And of course, if you want to know how to do all of those transformations, make sure you hit that like button, subscribe, leave your questions and feedback in the comments below, watch this video next, and I'll see you tomorrow.